Good morning, guys. Today we're going to work on the next part of Chapter 8, which is the section on special right triangles. There are two special cases that always pop up in trigonometry. They always pop up at least once on the ACT or any other kind of standardized test. And they require that you memorize two special cases. So you have some 8-2 notes that I handed out before we started our NTI days that you'll need to dig out. If not, you could always print the annotated ones that are in your Chapter 8 folder, your Unit 8 folder on Schoology, if you need to. So I'm going to take a little bit of a side trip first before we actually start writing anything in the notes. So just put your pencil down for a minute and let's look at a couple of these special cases before we really dig into the notes. So the first special case is called the isosceles right triangle. Isosceles means we have two equal sides, so we'll have to pretend this is a pretty picture. So this leg and this leg are equal, and there's a right angle between them. So when the two legs are equal, you can't have a hypotenuse equal because hypotenuse is always longer than your legs. When your two legs are equal, you get an isosceles right triangle. It's a special circumstance. And depending on how big those sides are, you can predict the hypotenuse really easily. So let's say that we have a leg that's 1. That means the other leg has to be 1. If I work out the Pythagorean theorem for the hypotenuse, and I'm just going to do this one time, and then I'm going to show you a really cool pattern. And I do 1 squared plus 1 squared equals x squared for the hypotenuse. 1 squared is 1, 1 squared is 1, 1 plus 1 is 2, is equal to x squared. And then I take the square root of each side. I'll get x equals the square root of 2. Now the square root of 2 is rather ugly. If I look at its decimal approximation in my calculator, let me get a clean screen here. Square root of 2 is about 1.414. So it's bigger than 1, smaller than 1.5. So it's definitely a bigger side than the legs are. So it's about 1.4. But we're going to keep it not ugly and call it square root of 2. Here's the cool thing about this triangle. It has two acute angles that are also equal because of the base angles theorem that we learned back in Chapter 5. So these two angles both have to be half of the remaining 90 degrees. So these are 45-degree angles. So the special case of a 45-45-90 triangle. This is basically half of a square, and this is just it's a special case where you have equal angles and equal legs. Turns out that if you scale that up or down, you get this really nice relationship. Let's say we doubled the length of each side. I'm not going to draw it quite to scale because I've only got so much space to work here. But if I made that triangle twice as big, a similar triangle to the original, it's still going to be a 45-degree, 45-degree, 90-degree triangle because similar triangles always have equal corresponding angles. We would still have two equal legs, and they would be twice as long as the original, so 2 and 2. It turns out if I work out the Pythagorean theorem for this case and simplify my result, when I'm finished, I'm going to end up with 2 times the square root of 2. 2 times the square root of 2. And if you'll notice, all that happens is you take your hypotenuse and you double it. So you stick your scale factor in front of square root of 2. You can do this with any scale factor. So I'm going to not draw this to scale because I don't have room. But if I had a triangle that were, say, 5 times bigger, it would still be a 45-90 triangle. And the sides would be 5 and 5 square roots of 2. Basically all I do is I take the original triangle and I multiply every side by 5. 1 times 5 is 5, 1 times 5 is 5, square root of 2 times 5 is 5 times square root of 2. Because remember, there's a times sign between the 5 and the square root of 2. All I have to do is multiply by a scale factor. You can do the same thing to scale it down. Let's say you want it half as big as the original. So you have a little triangle that's 45, 45, 90. I'm going to mark those congruent because it's easier to do that than it is to write the 45s in. Let's say this is half as big as the original. Half of 1 is a half. Half of 1 is a half. Half of radical 2 is half times radical 2, or we could say that's radical 2 divided by 2 if we multiply straight across and put it in a simpler form. So you can scale up or you can scale down. So here's the trick, the sort of the shortcut that some of you are going to catch on to. If you memorize this original one back here, which is what we all are going to have to do no matter what, then you can scale it up or down to find missing measures of sides of any other size of a 45, 45, 90 triangle. Okay, that's special case number 1. There's a second special case. And the second special case is what we get when we divide an equilateral triangle in half. So let me, again, you're not taking notes yet. We'll summarize this in our notes in just a minute. But this will make our notes less messy, and we won't worry so much about where it came from as what the facts are. So if we start with an equilateral triangle, so an equilateral triangle has 3 equal sides. Let's say they're all 2 units long for now. It'll just make it easier in the long run. This bottom side is 2 as well. 180 degrees total means each of these angles has to be 1/3 of that 180. So 60 degrees here, 60 degrees here, 60 degrees here is a total of 180. So I'm going to remember there's 60 up there. If I divide this triangle in half with, that's an angle bisector, it's a perpendicular bisector, it's an altitude, it's a median, all those special segments we discussed back in Unit 5. This is the same special segment for all of those. But I really want to just focus on one side of this, only on this side right here. This triangle is a 30 degree, 60 degree, 90 degree triangle. That's the other special case. You really have 2 of them back to back. I only want to look at one. The length of this hypotenuse is 2. The length of this short leg is 1. And if I do some Pythagorean theorem to find this third leg, x squared plus 1 squared equals 2 squared. So x squared plus 1 is 4. Subtract a 1, we get x squared equals 3. And then take a square root. X is equal to square root of 3. Square root of 3, let's see what that is as a decimal. It's going to be ugly, so we're not going to want to normally look at it as a decimal. But it's about 1.73. So it's longer than this leg, and it's shorter than the hypotenuse, which makes sense because the shortest leg should be opposite the smallest angle, so the 1 should be opposite the 30 degree angle. Square root of 3 is the middle-sized side, so it should be opposite the middle-sized angle, and then the right angle is the biggest angle of the triangle. It's opposite the hypotenuse. So we get this third triangle that has sides 1, 2, and square root of 3, and square root of 3 is the middle-sized side because it's about 1.7 units long. So this is the second special case, and like the first special case, you can scale it up or down. So if we take another 30, 60, 90 triangle, and we make it twice as big as this one, we're going to double every side. So if we double 1, we get a 2. If we double 2, we get a 4. If we double the radical 3, we get 2 times radical 3. So we can simply multiply by a scale factor of 2 and get new sides without having to redo the Pythagorean theorem. If we look at one that's, say, 7 times as big, and it's not drawn to scale, so just use your imagination. Same angles and similar triangles, and we want it to be 7 times as big as the original. The short leg is 1 times 7, or 7. The hypotenuse is 2 times 7, which is 14, so hypotenuse is always double the short leg. And then 7 times the long leg, radical 3, is 7 times radical 3. So it works very much the same way the 45, 45, 90 works. We just have a different set of numbers in our original triangle that we would scale up or scale down. So our first goal is to commit to memory the 2 special cases in their simplest form, and then learn to scale them up or down, either the short way or the long way, and I'm going to show you both methods. So now we can go back to the actual notes and do some examples. So in the notes, the first slide just is a quick preview of why we need these or when we use these. They provide shortcuts to bypass the Pythagorean theorem, and sometimes we don't have enough information to use the Pythagorean theorem. They're derived from a square and an equilateral triangle, which we just saw. They're used quite a bit in trigonometry, always show up on the ACT, and you have to memorize them. And of course, this expected quiz tomorrow, well, that's not going to happen, but we will have some practice today and practice tomorrow. So let's skip right to the big thing. Know your 2 triangles. So we just derived those on a scrap piece of paper. Now you need to pick up your pencil and actually write down these 2 special triangles. So first of all, we have the 45, 45, 90 triangle, and pretend that that's a beautiful picture. So we have 2 45-degree angles, 1 90-degree angle, and the legs have a length of 1 and 1, and the hypotenuse a length of square root of 2. You need to memorize this triangle, and we'll need to be able to draw it at a moment's notice and label the sides and angles appropriately. The orientation may change. You may turn it around in different directions, but this is our sort of basis triangle that we use to solve other triangles that are similar to this one. Commit that to memory. And then the second case, the 30, 60, 90. Let's get a picture of that one. So when we draw the 30, 60, 90, we want to try to draw it so that there's a shorter leg and a longer leg, unlike the last example where the 2 legs should be the same. The shortest leg is the 1. It should be opposite the 30-degree angle. The hypotenuse is the 2. It's the longest side. It should be opposite the right angle, the biggest angle. And then the third angle is 60 degrees, and opposite that should be the middle-sized side, which is radical 3. It is super important that you get the right sides and the right angles opposite each other. Little angle, opposite the short side. Big angle, opposite the biggest side. The most common mistake that students make is getting the sides labeled incorrectly with respect to those angles. My suggestion is when you use this triangle as a reference triangle, you draw it in the same orientation as the problem that you're working with, and you label your angles first, and then label the sides to correspond to them. This is the second and only other one that you need to memorize, because when you need them, you won't have they won't be given. You'll just have to be able to draw those on your own right out of your head. So we'll keep these handy for reference as we solve for missing sides of triangles. So here's what you have to be able to do with them. Look at problems such as this, where you have a 45, 45, 90 triangle. When you see 45, 45, 90, your brain will go, oh, that's a special case. I know something about that. And you will need to reference the 45, 45, 90 triangle that you have memorized, because you don't have the information that you typically would have to do Pythagorean theorem, because normally when we use Pythagorean theorem, we already know 2 sides. We don't already know 2 side lengths. We know 1 side length, 9. So instead of using the method that I used with Pythagorean theorem, the first step on this one is to draw the reference triangle that I have memorized. I want to turn it around the same direction as this one, right angle in the bottom left corner. These are 45-degree angles in the acute angle corners, and the one that I have memorized has legs of 1 and a hypotenuse of square root of 2. Now, there's a long way and a short way to solve for x and y. Some of you will be able to see the short way and not have to show any work at all. So here's the short way. Compare your reference triangle to the one you're trying to solve. It appears that this one is 9 times bigger than this one, which means every side is 9 times bigger. So 1 times 9 is 9, 1 times 9 is 9, so x is 9, and then multiply radical 2 by 9 to get y, and that's 9 times radical 2. Write the answers down, you're finished, you move on. So you could potentially solve for x and y with no work shown at all. So if you can do that, it's really quick, it's really easy, write down your answers, move on. For the rest of us who have trouble seeing that, we're going to write a proportion. We're going to solve it using some algebra. So let's say I want to solve for x first. So to solve for x, I need to compare it to its corresponding side of 1. So x is to 1 as, and then I need another pair of known sides. I only know 9 on this triangle. I'm going to have to use that one, and it corresponds to 1. So 9 is to 1. So we can make a proportion just like we did in chapter 7, and then cross multiply. X times 1 is x. 9 times 1 is 9. X equals 9. Done with x. Then to do y, we'll change colors. For y, we'll need to compare y to radical 2. Those are corresponding parts. So y is to radical 2 as, and then pick another set of sides. I would use 9 is to 1 again. So 9 is to 1. And cross multiply. Y times 1 is y. 9 times square root of 2 is 9 times square root of 2. Done. So it could be as simple as set up a proportion, cross multiply, be finished. Sometimes there's more work to it than that. We'll get to some of those. But all of this hinges on knowing that triangle and being able to draw it from your brain to the paper. Okay, let's take a look at another one. We'll look at another 45, 45, 90. Even though only one 45 is labeled, a 90 and a 45 make 135 degrees. There can only be 45 degrees left over for a total of 180. This is the 45, 45, 90 special case. I need to compare it to another 45, 45, 90. So I'm going to draw a 45, 45, 90 in the same orientation as the one that's given, so it's easier to compare corresponding sides. The legs make the right angle. Those have to be the ones. Hypotenuse is square root of 2. Now, if you're really savvy, you can look at the big triangle and the little triangle and decide that the big one is 20 times bigger than the small one. And you can say, okay, so that means x is 20 and y is 20 square root of 2. If you can do that, write down x equals 20, y equals 20 square root of 2, you're finished, and move on. If you can't see that, you've got to work it out. So if we want x, x corresponds to 1. X is to 1 as 20 is to 1. 20 is to 1. Cross multiply, x times 1 is x. 20 times 1 is 20. X equals 20. Short and sweet. Then we need to find y. So y is to square root of 2. Y is to square root of 2 as 20 is to 1. We use that pair again. Cross multiply. Y times 1 is y. 20 times radical 2 is 20 times radical 2. Finished. But again, being able to do the work hinges on having that triangle memorized. You have to memorize your special cases first. Okay, let's take a look at a couple of 30, 60, 90 examples. So on this next one, we have a 90-degree angle and a 60-degree angle labeled, which means the other angle has to be 30, because 30 plus 60 plus 90 equals 180. So I see this triangle on a standardized test, and I say, oh, that's a special case. That 30, 60, 90 is the one that Miss Rice said we had to have memorized. Okay, so I need a corresponding similar triangle that I have memorized, because I don't have enough information to use Pythagorean theorem here. You need two known sides, and I have two unknown and one known side. That's not enough information to use Pythagorean theorem. So I'm going to draw off to the side a triangle that looks just like this one. So I want to position it the same way, orient it the same way, put the right angle in the top corner, short leg over at the right side, long leg on the top left side, hypotenuse on the bottom. So turn it the same way and label your angles first. So smaller angle on the left bottom is 30 degrees. The bottom right corner is the middle-sized angle, 60 degrees. Angles should match. Get those labeled first. Then put your corresponding sides in the right positions. So 30 degrees is the smallest angle. Opposite 30 is this short leg. The shortest leg is 1. Of course, it should be kind of obvious that leg is shorter than this leg. The shorter one is always the 1. If you draw it roughly to scale, you'll be able to tell the difference between the short leg and the long leg. The hypotenuse is the longest side. That's down here on the bottom. It's opposite the right angle. That's the longest side. That's 2. That means this middle-sized radical 3 goes on the top left, opposite the 60-degree angle. Once you get those labeled correctly, you're ready to solve for x and y. So I'm going to do x first. X corresponds to radical 3. So x is to radical 3 as 14 is to 2. 14 is to 2. There's a little more work to do on this one. When we cross multiply, we're going to get x times 2, which is 2x. In the other direction, 14 times radical 3 is 14 times radical 3. We've got to do an extra step this time of dividing by this 2 to get x on a side by itself. So if I divide by 2, divide by 2, x is equal to 14 divided by 2 is 7. So we can divide out that common factor of 2, and we'll get 7 times square root of 3, and we don't have a fraction anymore. So 7 square root of 3. Now, to solve for y, y corresponds to 1. So y is to 1 as 14 is to 2 again. 14 is to 2. 14 is to 2. Y times 2 is 2y. Cross multiply. 1 times 14 is 14. Divide both sides by 2, and y is equal to 7 is your other missing side. Now, if you're pretty savvy, you may be able to look at these triangles and say, well, this hypotenuse is 2 and this hypotenuse is 14. This is 7 times bigger than this. So I've multiplied everything here by 7 to get this one. So multiply 1 by 7 to get 7. Multiply radical 3 by 7 to get 7 radical 3. And if you can see that, you can skip straight to these answers without actually having to set up equations and work them out. If you can do it without writing the equations, if you can just see, if you can just do it in your head, that's okay. That's a good skill. But this is your backup method if you can't just see it. So this is one of the rare cases where I will let you skip straight to an answer, because some of you can just multiply that in your head and be done with it. Okay, let's look at another 30, 60, 90 example. So 30, 60, 90 again. So we start with a reference triangle. Turn it around the same way, same orientation as this one. So right angle in the bottom right-hand corner. 30 in the bottom left-hand corner, 60 degrees in the top right-hand corner. Those should match. Opposite the 30 is the short leg. So over here on the right is the short leg of 1. The hypotenuse is the top longest side. That's always 2. Long leg is radical 3. Okay, now if you're savvy, you can look at the two triangles and see that the big one is 15 times bigger than the small one. So if you multiply everything by 15, you'll get a hypotenuse of 2 times 15, which is 30, and a long leg of 15 times square root of 3. If you can just do that in your head, write down your two answers, label them, be finished. If that's not obvious, let's work it out. So x goes with radical 3. X is to radical 3 as, and then I need 15 is to 1. 15 is to 1. Cross multiply. X times 1 is x. 15 times radical 3 is 15 times radical 3. X is on a side by itself. We're finished. Now let's go back and solve for y. Y corresponds to 2. So y is to 2 as 15 is to 1. We'll use that again. 15 is to 1. Cross multiply. Y times 1 is y. 15 times 2 is 30. Y equals 30. We're finished. So all of the examples we've seen so far do not involve any messy algebra. It's pretty straightforward. Those of you who can see it, see those scale factors and multiply in your head, you're going to find this to be really easy types of problems. Sometimes it's not quite this simple. Sometimes we have to rationalize a denominator, which is the process we learned to do yesterday. So we're going to look at a couple of examples before we finish that involve that messy process that does sometimes get involved. So 2 more examples, one of each type of triangle when you have to mess around with an irrational denominator. So we'll start with the 45, 45, 90. I see a 45, I see a 90, that means this other angle is 45, so my brain says, oh, that's a special case. I know one of those. And so I'm going to draw my reference triangle that I had memorized with a right angle in the bottom corner, 45 in the top left and the top right, same orientation as what's given. My legs are 1 and 1, hypotenuse is square root of 2. I know that because I have the triangle memorized. Until you get that triangle memorized, you'll need to jot it down over and over again. Practice is how you're going to memorize that. You just write it down lots and lots of times and it becomes second nature. Now, this one's a little more challenging because we have a scale factor that's a little bit messier. What do you do to square root of 2 to change it into a 16? Oh, it doesn't have a square root of 2 in it. That's not as simple as what we were doing in the last examples. So this might be a case where I want to actually set up a proportion and solve it, even if I do the others in my head. So let's just make a proportion. I need to find x. X is to 1. X is to 1 as 16 is to square root of 2. 16 is to the square root of 2. I didn't leave myself quite enough room here, so I'm probably going to have to actually, let me just rewrite it over here so that I have a little more room to maneuver. Okay. Now, cross multiply. X times square root of 2. Well, square root of 2 is just a number. Treat it like any other number. Okay. X times square root of 2, or you can say square root of 2 times x. Just make sure you don't put that x under the radical sign. Equals 1 times 16 is 16. And then we divide both sides by square root of 2 to get square root of 2 on the side by itself. So divide by square root of 2, divide by square root of 2. Square roots of 2 cancel on the left side, leave an x. On the other side, we have 16 over the square root of 2. Now, square root of 2 is not a 2. Square root of 2 is 1.414 blah, 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 some long, nasty, non-repeating, non-terminating decimal. So we can't divide that in the form that it's in. So it looks like I'm finished because I have x on a side by itself. However, on a multiple choice test, this would never be an answer choice because square roots in the denominator are considered bad form. So we would need to rationalize this, which is the process we learned to do yesterday. So what I think I'll do is just go over to the side, find some room in the margin, and rationalize that denominator. So let me go over here to this margin. I have some space, or even down here. How about I work right here? 16 over square root of 2 needs to be rationalized. The procedure is to multiply by a form of 1, square root of 2 over square root of 2. If we do that, we multiply straight across, 16 times square root of 2 on the top. On the bottom, square root of 2 times square root of 2 is 2. Then we simplify the factors outside the radical. So 16 and 2 will both divide by 2. 16 will divide by 2 8 times. 2 will divide by 2 1 time. That's going to simplify down to 8 times square root of 2 in the numerator. Understood 1 in the denominator, which I can drop. So the simplest radical form of x equals 16 over radical 2 is actually 8 times radical 2. So I did a little bit of work over here at the side. So the need to rationalize, that gets done there. And this is my final answer, which actually does turn out to be prettier than the unrationalized version because we eliminated the fraction. On a multiple choice test, that would be the answer choice you would have to look for. So this one's a little bit more work. The setup is the same as all the other problems. It's the simplifying that takes more time and more work. Just something we have to practice. Okay, we got one more example of a little messier problem like this with 30, 60, 90s, and we'll wrap it up for the day. So we have a 30, 60, 90. We'll go ahead and label my 30 right there. And I need to find two sides, x and y. I don't have enough information to use Pythagorean theorem, so I'm going to use the 30, 60, 90 triangle that I have memorized. So let's draw a triangle in the same orientation with a 30-degree angle, a 60-degree angle, and a 90-degree angle. And opposite the 30 is a 1, hypotenuse is 2, opposite the 60 is radical 3. And I know this because I have my triangle memorized. If you don't have yours memorized yet, look it up and practice it until you have it memorized. Okay, let's find x first. So x is to 2. X is to 2 as, okay, I have 4 radical 3 is to radical 3. 4 radical 3 is to radical 3. Okay, now before I cross multiply on this one, I noticed something that's really handy here. I have a common radical 3 on the top and the bottom. You can cancel out common factors. Cancel out that common factor of radical 3, and that's going to give us an understood 1 over 1. So if I rewrite that, that's actually x over 2 equals 4 over 1, which is a much nicer piece to work with. So sometimes we can simplify before we even multiply, cross multiply. It's going to make our work a lot easier. Now cross multiply, x times 1 is x, 2 times 4 is 8, x is equal to 8. Alright, one more and we're finished. Let's solve for y. Y goes with 1, so y is to 1 as 4 radical 3 is to radical 3. Once again, I'm going to cancel those radical 3's that I see, and I'm going to have y over 1 equals 4 over 1 when I rewrite it. And then y times 1 is y, 4 times 1 is 4, y equals 4 is our final answer. Okay, So as you work on your practice problems today and tomorrow, remember that the answer keys for these are in your Unit 8 folder. All of your answer keys are in that folder. And it is always a wise thing as you're working in your packet to go back and check your work as you go before you actually do that homework check quiz. If you'll check your work as you go, then you're not going to get any wrong answers on the homework quiz because you'll have checked your answers already. And email questions, message me questions if you have them, and then come back and look at examples as needed. You also have digital copies of these notes in your Unit 8 folder should you need just to see a prettier picture than maybe what you have on your own paper. Okay, so nothing new. Tomorrow you'll just practice some more, and then we'll be ready to start the last section of the chapter on Thursday. Hope everybody's healthy and doing well. Hang in there, and we'll keep on going.